Hi, this video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not a tutorial, just me learning game programming. Enjoy the video.
Greetings, coders, and welcome. First off, I would like to say that I have added to all the coding videos subtitles, because I figured the hearing impaired are helped by adding subtitles. So adding this will make the videos more accessible to an even larger group of people who otherwise wouldn't be able to follow what is going on. So now I have to say that the translation is automatic, which is impressive in itself, but it does make mistakes. So if I appear to, if you are using subtitles and I appear to say odd things, then I have to blame the automatic translation. That said, this episode is about something special that I understand almost completely, but not all the way. But it is a field, sort of a side thing that I don't feel is really necessary for us to know. Let me show you what I mean. I'm going to run the code as it is, and you will see the title screen, but it's changed slightly. And I will tell you right away that the top half of the screen now is in bitmap mode. I suppose that Georg wanted to do like a fancy title, because this, if you remember, perhaps we created 4 different characters and built this title just by placing characters on the screen. What you're looking at now is almost the same, but it is a bitmap. I can only assume that the bitmap data was taken from some sort of a tool, because there are some artifacts that are not supposed to be there. They are a different color and they are in odd places. But that is the part that I was talking about just now. I'm not so interested in the details of how to make a good-looking bitmap. I am interested in how I can make the screen split in half and have a part of it be in bitmap mode and the other just normal character mode. That is interesting. And before, I know I said that this game didn't have any raster interrupts. Well, now it does, and it sort of doesn't, because it does only have that in the title screen. As soon as the title screen is gone, when you go into the game, which I can't now because I don't have a controller attached, the whole raster interrupt is taken away. So how does it work? Let's have a look. We're going to confront the problem straight away, because what you are looking at is the bottom of the code, and you are looking at the tail of the bitmap data. Let's scroll up a little bit, and you can see a whole lot of data that came from somewhere. I don't really know. But this is the title logo bitmap data. I haven't worked out how much it is. It is 8 lines worth of data. So it's in normal character mode, it would be 320 bytes. This is obviously much more. And at the end, there's some free space, and then there's something else. And it has an effect. It has a color effect. It has a presence effect, but I'm not sure exactly what it is. So if you know more about bitmapping on the Commodore 64, then please tell me, because I haven't looked into it, so I can't tell you at this moment. What is interesting to see is where we are telling the assembler to place this data, because we've now, this directive, the asterisk, says to the assembler, okay, load this data at this specific memory address. As the comment says here, that prevents us from having to copy the data there, which of course is a time-consuming exercise, and we can just have the assembler do that. This is potentially dangerous if elsewhere in the code we assume this memory location to be free or available, because during load time this will just be placed there, and if we go there during runtime, then we may run into trouble. But as for now, there's no sign of that. Also, there is a table of color RAM data that we write there. Apparently, the color RAM works much the same in bitmap mode, but this is character oriented. So these are the 320 bytes. This is 10 lines of 32 zeros, which comes down to exactly 8 lines of because one line on the screen is 40 characters. Blah blah blah. This is basically to make the background black. So that works in character mode. And apparently also in bitmap mode. Now, when you start looking into these multicolor modes and bitmap and character mode, it's extremely complex. Probably it isn't when you've studied it enough. I haven't. But then again, that's what I said at the beginning. I'm not really interested in that at this point. Let's have a look at what I am interested in. I'm going to have to scroll back to the top of the code. Going to get my trusty meld tool as well. And scroll all the way up. And look at the first code change. Now, naturally, again, there's something. Oh, let's have a. We already had the double kernel labels. They're still there. And at line 156, here we are, 156. We had some nice labels here, and for some odd reason, they are changed to the specific addresses again. I suppose that during developing, I've addressed this before. When you're coding, you're constantly fighting, do I stick with these arbitrary names that I've given the labels? Do I remember the registers by their hexadecimal address? Do I remember them by their decimal, or maybe their decimal relative to the start of the VIC? You can see Georg struggling here as well. He's mixing them up, and maybe that is the best way. First, just do it the way that feels most comfortable while you're coding, and then change them to whatever you think is best. Now, you may not remember this. We went over this these settings. They haven't changed, by the way. They're still exactly the same. We've set the VIC bank to point at the last 16K bank in memory, and we have set the place where the character set is to be found. That hasn't changed, but we'll run back into that in a minute. Also new in the code 238. We're still setting up here 238. Okay. Now have a look at this. This has been added. Okay, this has been added. And this was already there. VIC control is D016. Over here we're using D016. So that is the same register. Here you can see that we're setting bit number 7654. Bit 4 is multicolor on. So we've set that to on, right? We've already done that because we're using multicolor characters. Multicolor on or off goes for text mode and bitmap mode, by the way. Now, we're doing something in bitmap mode, and lo and behold, this appears. And we're setting 18, hexadecimal 18 into VIC control. What does it do? Bit number 4 sets multicolor on, but it already was on. We turned that on just a little while ago. Bit number 3 is 40 column mode. So we're basically setting 40 column mode, which is the default mode and was already there. So this is kind of a slip up. This code isn't. I haven't tested this, but I am sure that if I removed this and saved and ran the code, it would do exactly the same. So this is a bit of code that isn't really necessary. This just goes to show that no matter how many times you read about this in the manuals, no matter how much time you spend trying to remember it, you cannot get this in your brain unless you are very special. I am not. So I have to look this up all the time, and I looked it up now, so it feels a bit like cheating. I know that Georg, he programmed this and he just put this in, probably under pressure of time or whatever, or he didn't want to go over it. All right, I have the luxury of being able to go over this code again and detect this. He's already done this, so he didn't have to do this. He just made sure that he did this right, but then he made a little mistake in the column mode, or maybe he wanted to put the column mode into 40 column mode. Whatever, I don't know. Then the title screen starts. This is new at this place. There's the wait frame. The wait frame makes us wait for the raster line to end up at the bottom of the screen. And then it does this. Init title IRQ. Oh Lord. There we go. Let's look at the rest of the title screen, because at the end of the title screen loop, there's the title loop, and this part is new. This bit is new. We're filling, as you can see, this title logo coloram, which were the 320 bytes at the bottom of the code that I just showed you, all the zeros. So we load the color data that is there. We store it in screen color. Remember, the color RAM at D800 never changes. It is always the same. We increase X. If it's not 0, we loop. So this does 255 repetitions. Then we start from location 256 and increase X until, this is a constant. We know it's 320 bytes. We already did 255, so we subtract that, and do the rest. Right? This is just 2 loops to copy 320 zeros to the color RAM. And then the regular title loop happens. Now let's look at that IRQ function, this init title IRQ. I'm going to scroll back up to the start of the title screen, and we're going to look at that. We're going to go to declaration. There we are. Now, if you are not versed at all in interrupt request handling, I'll give you a quick rundown. What happens in interrupt requests is that a device, an event, whatever, can cause an interrupt to happen. An interrupt is basically a request to the CPU to say, finish the command that you're working on, and as soon as you're done, jump to a different routine. And then at the end of that routine, we restore everything the way it was, and we continue where we left off. Now, if you are doing something that is very timing critical, then it is important to know the command that the CPU is executing at the moment that the interrupt request arrives. It may be a long or a short command. It can be anything from 2 cycles up to 7 cycles. Now, if you're very timing specific, you have to know about that. In this case, we don't. So, but let's continue. We first, we start by setting the interrupt flag, which means that during the setup, no interrupts can happen. This is done because we're going to change the interrupt vector, so we're going to tell the CPU where to jump in case of an interrupt. If an interrupt happens halfway during that process, the computer might crash, and it most likely will. So we have to make sure that while we're setting up the interrupt, nothing is going on. So there are no interrupts while we're doing that. We start off by telling the Commodore that we want the normal VIC registers available at this memory location. So D000 to D whatever. So we set hexadecimal 37 to register 01. This is the default value. So when you start your Commodore, we can have a look at that. Perhaps, do we need to? Yeah, maybe interesting. So if I'm just going to open the monitor and I'm going to say D01. Oh, it's too long. D000 to 10 05. See, 00 is 2F, 01 is 37. So the value of register 1 is 37 when you boot up the Commodore. I could have done that differently. It doesn't matter. So we're setting it back to default mode so that we're sure that we can reach, and there's no RAM or character ROM or color RAM or whatever. There's just the registers. Next, your Commodore has 2 complex interface adapters. Each of them contains timers, and they can generate interrupts. Now, we're doing our own interrupt, and we have nothing else going on, and we want to make sure that both of the CIAs are not generating interrupts. And this code doesn't do that. It just says to CIA number 1 that we don't want timer interrupts. So I didn't really look at which bit controls that. We might do that very quickly if we go to DC0D. There we are. I'm going to shove it into the screen. There we are, DC0D. I've looked it up and we're writing 7F in there. So we're taking the programmer's calculator. We say 7F. And I wonder if perhaps, okay, write bits, enable interrupts. Let's see, what are we doing? Are we writing? Yes, we're writing. We load 7F and we store that in DC0D. If you write that, enable interrupts, enable, enable. Fill bit. Bits 0 to 6 that are set to 1 get their values from this bit. Bit 0 is set to 0. Oh, okay. This is a fill bit. Oh, that's funny. Bits number 0 to 6 that are set to 1 get their values from this bit. So bits number 0 to 6 that are set to 0 are left unchanged. So if we set them all to 1 and then write a 0 to bit number 7, they all get 0, so they're all disabled. I didn't know that. That is a neat trick. So there's a load of interrupts that we can set, and apparently this is a way of setting them all off. Next, the VIC chip doesn't always generate raster interrupts. Now, very quickly, the raster is the point at which the VIC, or is basically the line at which the VIC chip is drawing at the moment. So there, depending on whether you are on a PAL Commodore or an NTSC one, there's a number of horizontal screen lines, and each one of them is called a raster line. And we can tell the VIC chip to generate an interrupt as soon as it hits a certain line. Now, in order to tell the VIC chip the line number, we need to be able to tell it a number that is higher than 255, because there are more than 255 lines. There are 312, as we can see here, on a PAL system. Therefore, we use the most significant bit of a different register, effectively giving us not 8 but 9 bits, which is enough to tell the VIC which it is. So first of all, we have to tell the VIC that we want to enable the raster interrupt request, which is bit number 0. Well, you can tell that bit number 0 is being set in this register. Then DO12 is the register that holds the raster line number. We want line number 16, which is basically the start of the third character line, counting from the border, so this is still behind the border. And the most significant bit of DO11 is the bit that we just talked about. So 1B is this number, the most significant bit is that one, and it is 0. So this actually means 16 and not 16 plus 255. So we've told the VIC to generate raster interrupts. We've told it to, we've told it at which line we want the raster interrupt to happen. Then we tell the CPU where to jump when this interrupt request happens. and this is an address. So we take the low part of this address and we write it to 0314. And the high part of this address goes to 0315. This set of addresses is called a vector, and this vector holds the address to where the CPU will jump. So by changing these values, just if you try this from the basic interpreter and change the value of this register, your computer will most definitely crash because it may happen right in the middle of a interrupt request. So before you mess with these guys, make sure that you know what you're doing. So we've turned interrupt requests off, and we're setting this address. So when this interrupt happens, this address is called. Now, when an interrupt happens from the CIAs, it's funny, by the way, that both of them are acknowledged here. We have to acknowledge them. If we don't acknowledge them, the Commodore is going to think that the interrupt request wasn't handled, and it's going to generate another interrupt. So you get a cascade of interrupts which you don't want. So at the end or at the beginning, you just you do that by reading the registers. These I/O mapped registers are magical in some ways. Sometimes simply reading them is enough to do something. So in this case, that is so. So we just read CIA1 and CIA2, and that is enough to acknowledge the interrupts. It's funny though that we didn't enable or disable CIA number 2, but we are acknowledging any interrupts from there. So we clear the interrupt flag. So from this moment on, interrupts are enabled again, and we return from this subroutine. Now, where was this done? Let's see, because I'm scrolling up. This was done here. We've just initialized the title screen IRQs. Excuse me. I'm going to take a sip of water. And at this moment, the title screen just happens. So we're clearing the screen and we're putting the title logo. But while this is happening, somewhere in this code, when the raster line is at the top of the screen, the interrupt is going to happen. And we'll see by looking at the code what exactly happens. Before I show you that, at the end of the title screen, which is here, this is the title loop, button not pressed, button released. When we do the restart, we do a wait frame just to prevent any flickering from happening. And then we say release title IRQ. Now we're going to look at that one first. Release title IRQ is the reverse of the setting, because we have to put things back to the way they were. So we do the same thing again. We set the memory map to the default value so that we are sure that we have the fixed registers at this location. We enable CIA number 1 again by writing this to that. We say that we want no more raster interrupt requests, so we set bit number 0 to 0. And look at this. This bit is important to look at. When you boot your Commodore 64, the interrupt vectors 314 and 315 will hold an address that points to EA31. That is a kernel routine. It handles cursor flashing and all kinds of things, and And at the end of this routine, it does a return from interrupt. We've talked about subroutines before, and a subroutine you can end with a return from subroutine. RTS reads an address of the stack and jumps back to that. When an interrupt happens, not only the address is pushed on the stack, but also the CPU status word. And with a return from interrupt, that status word is also restored so that the CPU can continue in exactly the same state that it was before the interrupt happened. So you have to end your own interrupt routines with an RTI. This routine does that. So this EA31 routine, remember that one because we're going to see that in a minute. But we're restoring it to the default. For good measure, we acknowledge any timer interrupts, and we're done. So this is the interrupt routine uninstalled. So that this happens at the end of the title screen when we exit the title screen and go into the game. But we still want to know what happens in this case. You know, what happens when the interrupt fires? Let's see. And there we go. We've just talked about acknowledging the CIA interrupts. We also have to acknowledge any VIC interrupt. Now we know that when we reach this code, the raster interrupt has happened, so we have to acknowledge it. In this case, we do that by loading the register and storing it back in there, and that is enough to... there are some other methods of doing this, like shifting the register left is a good one. Reading it and writing back to it is the way to tell the VIC chip that the interrupt has been handled and that it doesn't have to generate another one. Now, remember what we're doing. The top part of the screen has to be bitmap mode, and the bottom part has to be text mode. So the way that we're going to do this is that we've set the bitmap mode interrupt request at the top of the screen, so line 16. So when that happens, we set bitmap mode, but we have to make sure that at the end of that stretch that we want our bitmap mode to be, we want to go back to text mode. So we set up the next interrupt, right? And we do that in exactly the same way. So the same registers are going to get the address of another routine, which sets everything back to text mode. And we want to indicate a line where this happens. This is going to be line 71. And we are setting the most significant bit to 0 again, while we are also setting... hold on, I have to check this. Is that DO11? Was that true? Right, DO11, see? So that's the same register, happens to be the same register. So we're killing two birds with one stone here. We're setting the most significant bit to 0, and we're enabling bitmap mode, because bit number 5765, this one, enables bitmap mode. Now, something odd happens because we loaded our bitmap data to address 2000 hexadecimal. We have to tell the VIC about that. So, what we do, we switch the VIC back. Obviously, the memory that we've indicated the bitmap data to be loaded is in bank number 0. If you look at the project information for this project, I have a memory. It has a memory map, and at the start of that memory map, just a bit of text explaining how the memory setup works. As you can see, this may be confusing things too much. but the memory map, it doesn't even. I've included the VIC information, but not the memory map the memory map doesn't include the memory map information, so I should add that definitely, and I will. The VIC can look at only 16K at a time because of its smaller address bus. So we have to select which one it is. Now, at the start of the code, we switch the VIC to bank number 3, which is the end of memory. Now the bitmap information is at the start of memory, so we have to switch back to bank number 0, but only during the top part of the screen. So we load the content of this register, we AND it with this so that we're sure that these values are 0. Then we OR it with 3, this is 3, so that we're sure that only these 2 bits are 3, and 3 matches the value of bank number 0, which is this range of addresses, and we store it back. I'll quickly find the name of DD00. DD00. Oh, that is the CIA2, as you can see here. CIA2 serial bus RS232 and non-maskable interrupt control. See that? DD00. Port A, serial bus access. Anyway, we are DD00. Oh, VIC bank. See, bits 0 and 1 determine the VIC bank. As you can see, as the value grows from 0 to 1 to 2 to 3, the bank number drops. So 0 is 3, 3, 2, 1, 0, and 0, 1, 2, 3. So we've just changed it to 3, and 3 being bank 0 being this range of addresses, which is exactly what we wanted. And then DO18, again, this register allows us to control where the VIC looks for its memory map information. And it's about bits number 1 to 3. So we count with 0, so this bit doesn't count. But 1, 2, and 3, which is these boys, they determine where to look. Now, if I'm going to... I can... I'll show you the information that I used here. Bits number 1 to 3 in text mode, but we're not in text mode because we just set bitmap mode. And here we go. In bitmap mode, pointer to bitmap memory relative to VIC bank. Now, we've set bank to 0, and the value is 100. 100, value is 4, and that points to this range, and that is exactly where we put our bitmap data. So that is fortunate, but not by accident, of course. So we're pointing the VIC to look for the bitmap data at this address. Now, remember that I just talked about this EA31 address, and you were all confused when you were listening to me. This is our interrupt handling routine. So when the interrupt fires, we go to this address, and we have to end it with an RTI, return from interrupt. But we're not doing that. We are actually jumping to this address, because this address also, this is that kernel routine that is the default routine. It also handles updating the timers and everything. So if you don't want to mess with the system too much, you can jump to this routine, and at the end of EA31 is an RTI. So you don't have to worry about that. You could just RTI here, and it would work as well, but the system wants to update some things as well. So we're leaving things intact by jumping to this address, which is the default. But remember that we've also set this one. So this code starts executing on line 10. While we are busy doing all of this, the VIC chip in the background is still drawing. But we've told the VIC chip to look, where to look for the bitmap data. So it's pleasantly drawing the bitmap data. But we've also told it that when this line is hit, this line 71, that we want to go to this routine. And let's imagine that time has come. So we go to that declaration. Now, of course, we start with acknowledging the interrupt again, so that it doesn't happen twice. The first thing we do is set bitmap mode again, so that we are sure that when the raster line hits the top of the screen, we go back to bitmap mode. If we didn't do that, things would go wrong, so we have to set it. Where does that happen? Well, at line 10, just like the last time. Line 10 in DO12, 1B in DO11, the most significant bit, you know it. And we want to set the VIC bank back to 3, because what happens below the part where the bitmap was drawn, we want our character set back. And our character set is still sitting in this range. So we have to quickly tell the VIC, before you go on, go back to bank 3. So we did that. Also, we want to turn off bitmap mode. So I'm going to shove this back in just enough. So we're back in. We've disabled bitmap mode. By the way, we've done again 2 flies with one stone. 2 birds with one stone. In Dutch, we say 2 flies with one strike, actually. So I was mixing things up. Sorry. So we've disabled bitmap mode. Now we're in text mode again. So when we write something to DO18, we're looking at these 3 bits. Get back the 110. 110 is this. Which is correct, by the way, because if we add the VIC's base address, which is here, to the address that we're looking at here, because we're telling the VIC again where to look for the characters. If you add those up, you get to the information that is in the memory map, which is here. 3000, and you add it to C, you get this. C plus 3 is F, and F is exactly where we put our character. So basically, we've just restored the information again. And we can jump back to EA31, which we all know and love now. So, I hope that you were able to keep up, because it was, especially if you're not well versed in interrupt handling and bitmaps and everything, this may be a lot of information. So maybe go back over the video if you want to understand how it works. If you have questions, feel free to put them in the comment section, because I always read them and I always answer as quickly as I can. So I'm going to let you go. Thanks for watching. I'm going to upload this one, and I'll see you in the next one. Bye-bye.